Welcome. In this video, we are going to talk about functions in multiple representations. Now, we're going to start out talking about relations, which are really just any time you collect two sets of data or have two components to a piece of data and then put them into a single set. Usually, you're probably most familiar with the idea of an x and y coordinate. So I'll have this graph here, and I have a single point, so say it's right here. Now there's two parts to this point. There's the set of data in relation to its x value and its y. So this point would be identified as 1, 2, and 1. So we'd say that its placement on the coordinate axis is at 2x and 1y. So in the the relationship between those two variables is what builds this representation. Now this isn't the only representation you can use. So we're going to explore some other things that you can do that might actually help you analyze data in a more efficient manner, depending on what you want to do with it. So let's look at that. First thing we need to do is talk about domain and range. Now, when you saw the graph before, some people automatically set off in their brain and start thinking about y equals mx plus b, or the slope-intercept form of an equation. Now, you don't really have to know what this is, but you may have seen it before. That's why I'm using it as a reference point. In this case, we would say, let's pick one at random, y equals 3x plus 1. So graphically, this would start like right around here, and it'd probably go up and over. So you'd have something that looks a little bit like this. Now the nice thing about this form is that I can find any point that I want just by substituting in x values. As you can see, this sort of setup allows me to substitute in here, and then it produces this. So for instance, I want to know, well, what's this point right here at when x is equal to 1? So I'll just plug in, or substitute 1 in here. Not allowed to say plug in anymore. Sorry, math teachers. So 3 times 1 plus 1, well, 3 times 1 is 3, plus 1 more is 4. So what I found is that when I substituted a 1, I got a 4. So I'd say 1 point on this graph is 1 and 4. And we'll get back to these coordinate points here in just a second. But the idea behind this is that when I substitute the x in, I get a y. So we may identify, in general, what we would call x and y values. So I'll move this over here. We may call it x and y if we're on a graph. We may also refer to it as input versus output. Furthering that same talk, we may refer to the idea of domain and range. The domain values represent all the values that you could substitute in based on whatever the limitations are of the problem. Now, if it's a straight line like this, the domain is pretty much, it's unlimited. We would say maybe all real numbers, because it would go on forever. You can substitute any x you want. But in other situations where you have just dots, it doesn't really look like that. Now, in that case, the input values, we would call them values of the domain. Because these are basically what's already set up, because it's not reactive. It's doing its own thing. The x's will exist, they get substituted in, they're only defined by the problem, so the domain that it could possibly exist in. Now the range tells us how much that function or relation spreads out. So the output. When I substitute this in, what do I get on the other end? So the range values would be basically the y values. So just whatever is possible based on the function that we have set up, and then what we substitute in. That's kind of how that goes. And the other way that you could refer to this, if I have say a science experiment, is the perfect example of where you'd have a graph that looks like this, which incidentally enough is really just the first quadrant here. But I may say that over time I have fruit flies. So I might say fruit flies here, and I'll try to write it so it helps if the pen takes. So flies written in the worst possible way that you could deal with. And then on the bottom I may say hours. Well, those hours will pass regardless. So these are hours. 1, 2, 3. So in general, when you have fruit flies in the beginning, the number's really kind of low. And then all of a sudden it'll shoot up, and then you'll have a ton of them, and then eventually they die off. But just the general idea is The input, what we would be substituting in, would be the x values. But the hours will go on anyway. The hours will occur whether you're analyzing fruit flies or not. It's irrelevant. But without the number of hours, the importance of the number of flies is irrelevant. And I'm telling you this because another way that you could identify these would be independent and dependent variables. So this is the independent variable. That's what you input, and this is your dependent variable. The reason that the flies is a dependent variable, you could say, well, flies will exist anyway, but you have no reference point for them. In the experiment, the hour that you are recording the information is important to how many flies there are. If the number goes down, you would think that something is happening to the flies. You could tell without knowing, well, I have 1,000 flies. So what? Who cares? But if I have 1,000 flies this hour and last hour I had 2, you can see that the number is increasing. So it's used as a reference point. But anyway, these are one of the myriad ways that you could find this information. So let's just do a quick setup for domain and range. For me, I always think of the abbreviation for doctor because that's just how I think for some reason. So abbreviation for doctor is DR. So not DOC, that's the Old West. And then I just think, okay, XY. In fact, in a lot of my work, I'll write that together. That's just how I do things. So going over, looking at the coordinates, I'd say, okay, domain, range, domain, range, domain, range, domain, range, domain, range. So in order to show the domain values, I may say domain is equal to, and then I have a curvy bracket, and then I would put them, pick all the domain values and put them in a set. So -2, 3, 4, 6, and 7. It's usually good manners to put them in number order, so numerical. Range values, I would say -1, 4, 5, 6, and 8. So there are my domain and range values. Well, what does this have to do with anything down here? There are two types of data that you would likely collect over time. One of those is discrete data, and one of those is continuous data. Discrete data is sort of like there's breaking points. It's almost an idea of packaging. If you buy a shirt, you can only buy one. Say they're $10, so you buy one shirt, and this is 10, and this is 1. One shirt is $10. 2 shirts is $20. That sort of thing. But you'll notice there's little dots. In that situation, the domain value is represented by these kind of brackets set up. That's really the way that you want to do it, because discrete values have specific points. You can't have half of a shirt, so I wouldn't have broken up parts here. Now, continuous, if you buy vegetables in a store that by weight. So say I buy, I don't know, tomatoes. I may put the tomatoes in because it's $1 a pound. Well, I could put, half a pound of tomatoes in. I could put 3/4 of a pound. So that value would increase with a line. So I'd have continuous things. Curves may be that way. Your continuous may look like this. But in this sense, the one that we're really dealing with, domain and range values change. In this case, we just have to have a grouping. If there are no restrictions at all, I may say that the domain value is all real numbers, which is basically saying everything except imaginary numbers, which would never happen in any level you're dealing with here. And the domain value, or the range value, which would be the y's, you see the arrows, right? It means it goes off this up and down and left to right forever. We may say that's all real numbers as well. Or maybe if I had a line that stops right here for whatever reason. In this case, I may say the domain values, and this is -1. I may say the domain values are x is greater than or equal to -1, something like that. But that's the difference between continuous and discrete and how you show them. moving on. Now we're going to talk about 4 different ways to identify or what you might do with the data. The first is look at domain and range. The second is to look at a table, then to make a graph, and then to make a mapping diagram. Well, domain and range is pretty obvious. We've sort of done that already, so I'll just do domain. -2. If they repeat, you don't put them twice, by the way. -2, 0, 1, and 4. There we go. Range. My smallest one is 1, 4, 5, 6, and 8. For a table, I might have x and y values, and I'll put -2 and 4. To give myself a nice look, I might just put the x's in order. -2 and 1, 4 and 5, which I should have put down here. So I'll just erase these really fast if I can do it without destroying the table. There we go. 0 and 8, 1 and 6. So there's a table set up. The reason that you would use a table is it's really easy to see how things are progressing, if it's going up or down, that sort of thing. For a mapping for a graph, I would do the same thing I did. You've seen the graph before, so it shouldn't be anything new. I'll just set this one up. Pretend in your head that those are straight lines. I know it's harder than it would seem, because I'm not really the best at ever drawing straight lines. Maybe the worst. As you can see, it's not easy working with this pen either. So I have -2, so here, and I've got 1 at 1, 1 at 4, 0 and 8, so this thing should go up a while. Make a dot right there. 1 and 6, right here, and 4 and 5, right in there. So there's a graph setup, and then a mapping diagram. Now, the nice thing about a mapping diagram is it's really going to help us in just a second identify if the relation is a function. In order to do a mapping diagram, you just need to make 2 boxes. 1, 2. Then you need to place your domain values in the first box, and we're going to place the range values in the second. If a domain or range value repeats, you don't put it in there twice, only one time. So -2, 0, 1, and 4. On the other side, I'll deal with 1, 4, 5, 6, and 8. And now I'm just going to draw a line that allows me to go from from the domain to the matching range values. So -2 goes to 1, -2 goes to 4. And you can see this gives a clear idea that, hey, this domain value is going to this range value and this range value. 0 goes to 8, 1 goes to 6, and 4 goes to 5. So that's a mapping diagram. And those are the 4 basic representations.